Barna, who will tell us about sketching for edit distance.
Not sketching.
Sublinear algorithms.
Yes. Okay. I think we had a lot of sketching here. Yeah, makes sense. Okay, so I'm going to talk about sublinear algorithms for edit distance, and this is the picture for the sublinear algorithms program. And whenever like I go to Simon's, like any program is in Simon's, as always, I'm kind of amazed by the pictures of every workshop. They're so innovative and so nice. Anyway, so the work that I'm going to present today, there are multiple works, and they are joint work with Elazar Goldenberg, Tomasz Kosiumaka, and Robi Krautkammer. Since this is the last talk of the Sublinear Bootcamp workshop, I don't need to motivate sublinear algorithms. Obviously, massive size, you could have access control, you just need an estimate. Most data is not useful anyway, so there could be multiple reasons to study sublinear time algorithms. So now, like, where the sublinear time algorithms appears, at least like when I, it could be like in my research, or there are 4 different areas where I have encountered sublinear time algorithms. So I just thought about showing these different aspects of sublinear time algorithms. So one is property testing, which is kind of like where sublinear time algorithms originated. So where you want to know whether your data belongs to a hypothesis class or is very far away from it. So that's property testing. Tolerant testing is more like in the flavor of approximation algorithms, where you are trying to estimate something, but you want to know whether it's not like whether it's satisfying a property and far away from it, but where you want to know whether it's within a certain approximation factor of it. Streaming and sketching, it handles data streams. Their main focus is on sublinear time space complexity, but sublinear time space complexity often also leads to sublinear update time. So sublinear time algorithms kind of plays a role in streaming and sketching as well. And the other part is dynamic algorithms, where your data is changing and you have to update your solution as the data changes. And there, one of the main focus is like you want to have your update time to be sublinear. So sublinear time algorithms appears in all these kind of aspects. So today we are going to look at edit distance. And if you look at edit distance, you can think about property testing for edit distance, tolerant testing for edit distance, streaming sketching for edit distance, and also dynamic algorithms for edit distance. And in all of that, sublinear algorithms plays a role. So what is the property testing version of edit distance? There you are trying to know whether edit distance between 2 strings x and y is close, like less than k is a parameter, or it's very far away, it's very close to epsilon n. In tolerant testing, you are asking whether the edit distance is less than k or it's greater than alpha times k, where alpha is your approximation factor, or this is what we call gap edit distance. In streaming and sketching, you want to do a sketching of x, you want to have a sketch of x, you want to have a sketch of y, and based on the sketches, you want to compute your edit distance. Again, the sketches are small, so here your time requirement is likely going to be sublinear. And in dynamic data, you have some dynamic data structure for x and y. There are some updates happens on x, updates happens on y, and you have to return your edit distance estimate for x and y. Okay, as the updates are coming. So again, here there had been some work here in dynamic edit distance computation as well, and the goal here is to get a sublinear time update time. So these are some of the references. Like there had been work in all these 4 aspects in edit distance computation. So what we are going to focus today is mostly over here, like where we are trying to know whether edit distance between 2 strings is less than equal to k or greater than alpha k. So what is edit distance? I'm pretty sure all of you know what is edit distance. So it's a very fundamental measure of sequence similarity. You are given 2 strings, x and y, and you want to do minimum number of insertion, deletions, and substitutions. And with that, you want to change your string x to y. So for example, here, given these 2 strings x and y, you can do So you can delete this B, you can substitute this B with an A, you can do 2 substitutions here, and then you can insert a B over here. So with 4 edits, you can convert X to Y. So the edit distance is 4. You could have done Hamming distance as well, but if you compute the Hamming distance between X and Y, so Hamming distance only allows substitutions. So Hamming distance between X and Y would have been 12. So its edit distance is more versatile than Hamming distance because Hamming distance allows substitutions, edit distance allows insertion, deletion, and substitutions. It has a lot of applications in bioinformatics, natural language processing, and so on. And it can be computed in order of n squared time, where n is your string length. So these are all the basics that all of you probably already know. And how do you get an n squared running time for edit distance? It's a simple dynamic programming. So you have a dynamic programming table. Each of these indices are computing the edit distance between for a prefix of length x and prefix of length y. This will be the edit distance computation here. So how do you compute the edit distance? You look at whatever is over here. Then these diagonal entry implies that whether these 2 characters match or not. Based on that, you come over here, and these 2 horizontal and vertical entry corresponds to insertion or deletions. So you have an n squared table, and each computation of each of the cell requires constant time. So overall, you get an n squared running time. And there has been some improvement over this n squared running time, but only in polylog factor. And also there is very good reason why you cannot get better than any improvement beyond this polylog factor, because if you do, then it will violate the strong exponential time hypothesis, and this is one of the cornerstone result of fine-grained complexity. Piotr is one of the author for who proved that any truly subquadratic algorithm for edit distance will violate the strong exponential time hypothesis. Consequently, there has been a long line of work on approximation algorithms. Since you cannot get an exact algorithm in subquadratic time, so there has been a long line of work on approximation algorithms and getting a faster running time than n squared. Typical holy grail here is to get a near linear time algorithm, and right now we do have a near linear time algorithm for computing edit distance, which approximates it within a constant factor. But today we are going to talk about sublinear time edit distance approximation. And in this case, what we have random access to x and y, and our results are going to be all randomized algorithms in Monte Carlo randomization. And sublinear time is required because even testing whether x is equal to y would otherwise require, sublinear time exact algorithm is not obviously possible because even testing requires omega n time. And the gap edit distance problem, as I had mentioned, that you want to distinguish between whether okay. So there is a typo here. So whether the yes version is whether edit distance is less than k, the no version is whether the edit distance is greater than some k prime, and in between k and k prime, you can return anything. So that's the gap version. Okay. And for our presentation, what we are going to focus is when this upper bound, this k prime, is k squared. Okay, so the problem that we are going to study here is whether given 2 strings x and y, whether the edit distance between these 2 strings is less than k is a parameter, or whether the edit distance is greater than k squared. So that's the gap edit distance problem. It's called quadratic gap edit distance problem. That's what we are going to study. Of course, you could have considered its k square is nothing special. You could have considered anything else, but just for simplicity, we are going to consider that. Okay, so now when you want to solve this gap edit distance problem, maybe the very first thing is to try uniform random sampling. And uniform random sampling just doesn't work for edit distance. And the uniform random sampling is enough for having distance, but it doesn't work for edit distance because, for example, here is a case where x and y, the edit distance is really, really large. If you do uniform random sampling, you will also see the edit distance to be really large. But here there is this case, you have this x and y is just a little shifted version of x. So the edit distance here is 2, but if you do random sampling over here, you will still your sampled edit distance will be really high. So you cannot really do uniform random sampling and hope to get anything for edit distance in sublinear. So this is the history of gap edit distance. And all the results that I'm showing here again is for k versus k square. But all these you can, if you can change the parameters and all of these, all of the, like there will be different versions of the results if you consider k versus not k square, but k to the c, where c is greater than 1. So the very first result came in 2003, and Ronit is here. So this is one of Ronit's work where they could distinguish. So this is more like in the framework of property testing, where you are trying to distinguish whether the edit distance is less than k or greater than epsilon n. So this is what they could get is k squared n plus square root of k, and this bound is also optimal. But it could only distinguish between k versus n. Then in 2009, Andoni and Onak, and also one of the authors here, they give an algorithm like which works for not just k versus epsilon n, but it works for other parameters as well. And this is what they got. So the focus of this paper in 2009, the focus of that paper was mostly about coming up with near linear time algorithm for subpolynomial approximation of edit distance. The focus of that paper was not on sublinear time algorithms. Yeah.
So the k versus epsilon case, should we think of it as smaller than epsilon or larger than epsilon?
K versus epsilon n.
Yeah.
Epsilon you can think about constant.
So k is smaller or?
K is the smaller one, yes. So if your edit distance is less than or equal to k, you can think about the strings are close by. So 2009, this is a result of Andoni Onak, where they could distinguish between k versus k squared, and this is the time that it would take. But this was at that time, 2009, 2010, or actually from early 2000 to 2010, the main focus was on getting near linear time algorithm and getting good approximation for edit distance. So the sublinear time algorithm for edit distance was picked up by us in 2019, where we gave an algorithm for k versus k squared, which has this running time n over k plus kq. And then after that, there has been a lot of work here. And a lot of improvements came in pretty quick sequence. So in 2020, we improved from n over k plus k cubed to n over k plus k squared. Again, as you could see, these are efficient for small k. Well, if it's small k, then it will become n. But you can think about, because of these polynomial factors in k, that's why I have written it's efficient for small k. If you plot it against these other two results, it will be clear that these are, like when k is small, these are better. And after that, so this was like n over k plus k squared. And another interesting fact about these results, the first two results were non-adaptive. So non-adaptive means like you are sampling before even looking at the strings. So you are doing your sampling in one shot. The next two results in 2019 and 2020, the sampling algorithm was adaptive. So we are actually looking at the results of previous sampling, and then we are deciding which part of the string to sample. So they were adaptive algorithms. So then in 2022, like this is, so there were these, one thing that was like kind of annoying over here is like we have a dependence of n over k, right? And if you were trying to solve the Hamming distance where for k versus k squared, you would have got n over k squared. And here we are getting n over k. So that was partially resolved in 2022, where the dependence from n over k was improved to n over k squared, but at the cost of a larger polynomial dependency on k. And then there was this another factor on n as well. So this result was efficient for even smaller k, because even for really when k was less than n to the 0.1, this result was actually matching the Hamming distance bound. But beyond n to the 0.1, it was not. So it was still adaptive. In the same year, we had another result where we resolved the non-adaptive complexity for edit distance. So for non-adaptive algorithms, we could get n over k times square root of k. And as you could see here, there is no polynomial dependency on k over here. So all the adaptive algorithms had polynomial dependency on k. Previously, the non-adaptive algorithms, well, these had some dependency, but they didn't have any polynomial dependency on k. And our non-adaptive algorithm also didn't have any polynomial dependency on k, and moreover, this is optimal. So there is a lower bound that matches it. And this is good for efficient for medium and large k and optimal for non-adaptive algorithms. And finally, this is this year, so that 2024, where there had been further improvement over this stock 22 result, where the polynomial dependency on k to the 4 has been improved to k square. This n to the 0.8 is now square root of n square root of k. So this is kind of the state of gap edit distance. So maybe it's better to show me, better for me to show you these results in a plot. So this is how it looks like in a plot. So the x-axis is k and the y-axis is the time. So this one is kind of the baseline. This is a linear time algorithm of Landau and Vishkin. In linear time, you can n plus k squared, you can solve the edit distance problem exactly. So that's our baseline. This is the 2003 paper by Ronit and others. And here we are plotting k versus k squared. So it only works for, and for that paper, your k squared has to be n. So this only works when k is square root of n, and they get a running time of n to the 1/4 here. Okay, so that's kind of one point in the plot. So Andoni-Onak's result. So it goes. So this is what you can get with Andoni-Onak's result. So this is how it looks like. So it doesn't get to. So it doesn't matches the 2003 result. 2003 result is optimal. So this result was not optimal. So this is the first result from 2019, which uses adaptivity, and you see this kind of there is a point where it's minimum and then it's going up because of the polynomial dependency on k. So that's why you see this kind of trend. This is the 2020 result, which improved beyond that, and now we have a different point, which is minimum. Before that point happened to be the maximum. So after this work, so this was the status of gap edit distance in 2020, and after that there were a few open questions that we wanted to know. So one was, can we remove the polynomial dependency on k? Because in 2019 and 2020 results that we had, there was this polynomial dependency on k. So that was removed by our non-adaptive algorithm. And the other question was whether we could meet the Hamming distance bound. And that was partially answered by this stock 22 paper and then improvement in Soda 24 for small values of k. So this is what it looks like now. Yes.
Quick question. So by non-adaptive, you mean just random sampling?
No, non-adaptive doesn't mean to be like it doesn't have to be uniform random sampling. It could be any other kinds of sampling, but it's just that you cannot look at the string or cannot look at the results of your other previous sampling steps to decide the next sampling step. So this is the current state of the art for gap edit distances.
So in the previous slide, you had ordinary k versus k to the c. What's particular about k squared?
Oh, right. So what particular about k squared? Yeah. We like this quadratic gap edit distance problem. There are a couple of reasons for why k versus k squared we thought it's kind of fundamental. So one was like for embedding from edit distance to Hamming distance, we see this kind of quadratic blow up. So k versus k squared. And another one, like if you think about in linear time, you are getting this n plus k squared algorithm. So there also, like, we really do not know for all values of k to get anything better than k versus k squared, even in linear time, when you allow linear time. So there were two reasons why we looked at k versus k squared, but all our algorithms work when it's less than 2. Okay, so this is the state of the gap edit distance right now. So this red line is the lower bound. So this up to this point, it's coming from having distance or Ulam distance lower bound. So we really cannot do anything over here. This is coming from the 2003 paper, so we cannot really do anything over here. This orange line is our work from 2022. This is the lower bound for non-adaptive. And we have an algorithm, like we have a result which matches the query complexity of this lower bound. So this is your non-adaptive lower bound. You cannot do anything better than here. Right now with adaptive, this is what you can do. This is the best result with adaptive bounds. So this part is kind of the unknown part. We do not know what's happening over there. So this sky blue region is unknown. We do not know whether using adaptivity you can go below this orange line and meet the red line.
If I only measure query complexity, don't care about time, then can we do anything in the blue region?
We don't know. Okay, so for all of these results, except for this one, the query complexity and time complexity matches. For this one, query complexity does match with time complexity if you're considering k versus k squared or k versus k to the 1.5. But if you want to consider k versus less than k to the 1.5, actually there is still a gap, and that's an open question here. So we do show a query complexity upper and lower bound for non-adaptive thing, but there is still some open questions if you're thinking about time complexity. And yeah, we do not know, even using query complexity, whether we can do resolve. This blue region remains unresolved as of now. And each of these sublinear algorithms were kind of motivated and borrowed techniques from the development that happened in approximating edit distance. So our first two results from 2019 and 2020, the ideas came from the exact algorithm by Landu-Vishkin from 1998. Our non-adaptive results of n over k, the ideas came from Andoni and Onak's 2009 paper. And also this improvement, which is the optimal for non-adaptive algorithms. So the ideas came from the 2009 paper, but also this 2003 paper. And the final two results, which are adaptive and matches the Hamming distance bound for small values of k, the ideas of that came from Andoni Krautgammer and Onak's paper from 2010. So the development in approximating edit distance has heavily, or even linear time algorithms for edit distance, have heavily influenced the development of sublinear time algorithms. So let me just briefly mention what is the state of art for approximating edit distance. So you can compute it exactly in n squared time, cannot do anything better than in n squared time for exact computation. Landu-Vishkin's algorithm runs in n plus k squared time. So this is linear if k is less than equal to square root of n. So these are all for exact computations. For approximate computations, Andoni Onak's result from 2009, it gives a sub-polynomial approximation in linear time or in polylog n time. Andoni Krautgammer and Onak's result from 2010, it gives a near linear time running time and polylog n approximation. That was a breakthrough at that time because people had been really trying to get into the polylogarithmic regime. Then in 2018, we have a subquadratic algorithm which gives a constant factor approximation. Best approximation factor is 3 plus epsilon. It's from one of my work. And then Andoni Nozaski's result from 2020, it gives a near linear time running time or constant approximation factor. So this is the state of the art for approximating edit distance. We still do not know how to use these results for development of sublinear time algorithms, but all of these before, like the Neonext 2010 result, 2009 result, they have all helped us to develop good sublinear time algorithms.
So the running time for the second to last, does it depend on epsilon, or is there?
Second to last? Oh yeah, there are some dependency on epsilon. Yeah, 1 plus 1.6 plus epsilon. Okay. So in today's talk, the results that I'm going to show you are these two results, this one, and I will give you some ideas about this. So I'm not going to talk about these adaptive algorithms which matches the Hamming distance bound for small k. And these are slightly older results. There are a few reasons why I selected to present this subset of results instead of the others. One of the reasons is like I'm one of the authors in these results. I know these results better than the other two work. But the other reasons are, as you could see in all adaptive algorithms, so this is adaptive, this is adaptive, this is adaptive, this is adaptive. There is a polynomial dependency on k. And that's kind of holding us from matching the Hamming distance bound. So I want to give you some idea like where this polynomial dependency on k comes up. And I hope by looking at these results, you will get an idea of that. And that's exactly how like this polynomial dependency on k comes up even in later works. And this one, this is really simple. And it already improves upon the previous adaptive algorithms. So it's so simple that I want to present it. And obviously, non-adaptive algorithms are oftentimes like they are preferred. So in some sense, like these are incomparable results from adaptive ones. I wanted to give you some flavor of how to design non-adaptive algorithms and get this. So I'll start with this n over k plus k cubed, k squared, these bunch of results, and they heavily depends on these Landu-Vishkin's result from 98. So let me just briefly tell you how Landu-Vishkin's edit distance algorithm works and then go into the sublinear time algorithm. Any questions about the state of the art or gap edit distance?
What is used in practice?
Okay, so that's another very good point. So this algorithm, I do believe, is very simple. I don't know what is used in practice, but this is very simple. Anybody can implement it in practice. This is also very simple. You can also implement it in practice. Rest, I don't know like whether anybody would want to implement it or not. Actually, this is also fine. So that's another motivation to show you because these are simple algorithms. So actually, I can tell you a little bit more in the time that I have. Okay. So Landu and Vishkin's algorithm from 1998, it gives you an exact algorithm for computing edit distance in n plus k squared time. And this is how it works. So you again have the dynamic programming table for edit distance. You have x and y, x here, y over there. And as you know, that the entry x and y computes the edit distance between the prefix 0 to x and prefix 0 to y. So you can also observe from this dynamic programming table that if you look at any diagonal, the edit distance actually monotonically increases or is monotonically non-decreasing. So you can, for every diagonal, you can compute the max row. Like we can compute the farthest I valued cell on each diagonal, where I is from 0 to k. So here you are trying to test whether edit distance is less than k or not. So what you are trying to do for every diagonal, you want to know how far can I go with a value of 0, with a value of 1, with a value of 2, with a value of k. Okay, and that's well defined because the values in any diagonal is monotonically non-decreasing. So that's what the algorithm and Landu and Vishkin are going to do. So it's going to compute the farthest I valued cell on each diagonal. So it starts with the main diagonal. So with 0, how far can you go? You can match A and B here, so you can go up to here. But after that, there is a mismatch. So you have to pay some cost over here. Right? So you can either decide to substitute here A with a B, so you pay a cost of 1, or you can decide to delete B and you move over here, or delete A and you move over here. So now you have this main diagonal, but you also have two other neighboring diagonals. So now that you have reached 1, now you are trying to see how far you can go with the value of 1. So here on this diagonal, you can go up to here. So everything matches, like B matches with B and so on. So you can go up to here. On this diagonal, you move over here and so on. So after that, if you have to move on this diagonal, you have to pay another substitution cost, or you can do deletion on X, deletion on Y. You can move over here, deletion on X, deletion on Y, and substitution on this diagonal. So this is how the tools look like. And then you are trying to move, how far can I go without any more errors. Here you get stuck immediately, because if you are trying to match, this will not match, so you get stuck over here and so on. And here you can go further. After that, you are looking at value 3. And with value 3, you can, in fact, reach the bottommost corner here. So the edit distance between X and Y in this example is 3. And what are you doing over here? So you're trying to find out whether edit distance is below K or not. So you know all your computations will be within the K diagonals above and below the main diagonal. Because anything above K diagonals, above the main diagonal, will have a value greater than K. And similarly, anything below the Kth diagonal will also have value more than K. So your computation is content in this band of 2K plus 1 diagonal, main diagonal, and K diagonals on the top, K diagonals below it. And in each diagonal, you are computing how far, like what is the farthest you can go with a value of 0, 1, 2K. Right? Now here, when you see 1, you are trying to see how far can I go without any mismatch. Here you see a 2, you are trying to find out how far can I go without any mismatch. So these are called longest common extension queries. So these are called LCE queries in short. So how many LCE queries are you making? So there are 2K plus 1 diagonals. In every diagonal, you are making at most K LCE queries for each value of 0, 1 to K. Right? So overall, you are making about 2K square LCE query. So what Landau and Vishkin showed that you can actually pre-process the entire string in linear time, so that when you have to make an LCE query, that those queries can be answered in constant time. And therefore, your running time for this is linear for pre-processing and constant for K order of K square LCE queries, and that gives you an N plus K square. And this is your path which you will follow to get the edit distance between the two strings. So for longest common extension queries, in constant time you can answer those if you allow for ordering time. Okay, so this is the algorithm that kind of motivated us to design our first sublinear time algorithm. So we are going to follow Landau and Vishkin's algorithm. So what could be a very natural extension of Landau and Vishkin's algorithm? So it could be like previously in Landau and Vishkin's algorithm, we were computing the LCE queries exactly. Right? So here now we can allow some errors. So we are trying to solve K versus K squared. So previously, our LCE queries, each of these LCE queries should not have any errors. But if we are trying to solve the K versus K square gap edit distance problem, then each of these LCE queries, we can allow for K errors. right? So instead of computing exact LC queries, we can attempt to compute approximate LC queries, where we'll still go without like, so let's take an example here. Like if we had considered exact LC query, I would have stopped over here. But I'm now allowing approximate LC query, so which is allowing me to go a little bit further, which is fine because I'm not trying to solve the problem exactly. I'm trying to solve the K versus K square in that distance. So I'm allowing these few errors up to K errors per LC query. So here now I get 1. I'm trying to move as far as I can with these approximate LC queries. And then I get 2. I'm again trying to move as far as I can with approximate LC queries. And now with 2 edits, like with, now I reach, using these 2, with a value of 2, I reach the bottom, bottom corner. And I will return that my edit distance is 2. What does it guarantee? First of all, if my edit distance is actually less than K, then I will reach here with a value no more than K, because I am only allowing approximate LC queries. So then I will be returning yes, so which is fine. But if I am returning yes, if my algorithm returns yes, that means I'm reaching here with a value of less than K, and there is some path which I'm following. And in each of these paths, I'm hiding at most K errors. And there are K such chunks, right? Like there are K such approximate LC queries in this path. So I'm at most hiding K square errors. So if I'm returning yes, then I'm also guaranteed that my edit distance is below K square. So I'm fine as long as I can compute this approximate LC queries. The correctness wise, I'm fine. So the question is, what is the query complexity for this approximate LC query computation? If you, so naive implementation is okay. So n plus k squared, like you can just do Landu-Vishkin, you don't have to do approximate. But still, the naive implementation, if you think about it, so here the computations are within 2k plus 1 diagonals. Each diagonal has n entries. So overall, the total number of entries is order of nk, right? You are trying to hide at most k errors per LC query. So that means you have to sample at a rate of 1 over k. So a naive implementation would be like, okay, nk entries, if I'm sampling at a rate of 1 over k, I'll still get order of n. So what we instead could do, like we instead could show that it's okay, it's enough to do a global sampling of n over k. So the global sampling somehow doesn't look at the dynamic programming table. It looks at the string and it's doing some global sampling. But we have to do some local sampling as well. So we have to pay some order of k sampling cost each time, like for each position where we are trying to query this approximate, where we are trying to compute this approximate LCEs. And how many approximate LCEs you are trying to compute? Again, there are order of k diagonals. Per diagonal, you might be computing k approximate LC queries. So for each of them, you have to pay these. So overall total order of k square LC queries. For each of them, you will be doing this local sampling of k entries. So that will give you a query complexity of order of k. Okay, and this local sampling obviously depends on where in each position I'm trying to compute the LC query. It's very much adaptive. So that's where the adaptivity comes in, and that's also where you are getting this polynomial dependency on k. Okay, so this n over k plus k cube. And then in our subsequent work, in our subsequent work in Fox 20, we improved these n over k plus k cube to n over k plus k square. And how did we do that? So here we said that we are spending k times, we are query complexity of k for k square LC queries. If I can reduce the number of LC queries from k squared to k, then that will automatically reduce my polynomial dependency on k from k cube to k square. right? So that's exactly what we did in our Fox 20 paper. So what we said that here, instead of doing the LC query on each of these diagonal, like align all these queries with the farthest column that you can get. So what we are doing here, like instead of computing the LC query from these 3 diagonals here, we will just do an LC query. We'll just align all of these on this diagonal, which is the farthest I can go using any of these k diagonals, and I will do an LC query starting from here. Okay. So similarly over here, instead of doing an LC query from all these parts, I will see where I can go the farthest using these diagonals, and only from there I will do one LC query. How does that help? First of all, it reduces the number of LC queries that you are doing. So when you are getting stuck at 1, you are doing one LC query. You are getting stuck at 2, you are doing another LC query. You are getting stuck at k minus 1, you are doing another LC query. So the total number of LC queries now reduces from k squared to k. So therefore, your query complexity improves from k cube. Polynomial dependency on query complexity improved from k cube to k squared. And why does it okay? Like, why doesn't it violate our correctness? Is because we are allowed to have this k versus k squared gap. So what are we doing here? Here we are aligning kind of, we are saying, hey, instead of using this diagonal, let's just move over here. Right? Let's just move over here. So, and that incurs that means we are doing some shifts. Insertion, deletion here. But how many insertion and deletions are we doing? At most k. So we will be stopping at most k times. In order to align these diagonals, we may be paying an extra k because of insertion deletion. So that's altogether that will still add up to k squared. So there are k such LC queries where we are hiding k edits. So k squared from hiding the errors in the LC queries. K for aligning each time you are getting stuck, but you will be getting stuck at most k times. So for insertion deletion error is at most k squared. So altogether we are still within this order of k squared bound. So correctness wise we are still doing okay, but we could reduce the number of LC queries from k squared to k. Okay, so if edit distance xy is less than equal to k, yes. If it's yes, we are still order k squared because whatever we have paid here to align the diagonals is still within my k squared budget. And that helps us to reduce the query complexity from n over k plus k cubed to n over k plus k squared. Okay. So let me now tell you a little bit more like why we need to spend this k query complexity every time you have to compute the LC query. Okay. So when you have to compute the LC query, if we are looking at it's possible that if you look at Landau and Vishkin's execution, then there are multiple diagonals using which your computation can proceed. Right? One of the diagonal might be optimum one, but it's possible that in that particular, when you are trying to do, for example, here with all ones, there are multiple diagonals through which you can proceed. And if you have to check every diagonal separately using random sampling, then it will be too much. You don't want to do that. Right? But one fact that we observed that if it indeed the case that there are multiple diagonals through which you can proceed your computation, then in fact the string that we are looking at over there, x and y, are both periodic in nature. It's because it's periodic, that's why multiple diagonals are good at that point. Otherwise, there would have been only one diagonal which would have been good. And I could have just sampled on that diagonal And that would have given me n over k overall query complexity. So the fact that if there are multiple diagonals which are good, that can only happen when the string is periodic. So instead of checking each diagonal, what we can do, we can instead check whether the strings over here are periodic or not. And when the periodicity breaks, it will kind of tell us, okay, so most of the diagonals are bad, there is only one diagonal, and I can just sample along that diagonal. So that's kind of the main idea here. Okay, so multiple diagonals good means the pattern is periodic. Instead of checking for each diagonal separately, we can just check for periodicity. And interestingly, what we show that, okay, so if there are multiple diagonals, we'll be checking for periodicity. And when periodicity breaks, when our check for periodicity breaks, there could be only one possible diagonal using which you can still proceed. And then if there is just one diagonal, then it's good because we can just do random sampling on that diagonal. So here is a little bit more details on how periodicity helps. So if I'm looking at x and y, suppose there are multiple diagonals for which it's good. So that means like y is also periodic, right? And moreover, if it happens that that periodic pattern breaks, that it starts to affect all the diagonals except possibly for one. So here it affecting this diagonal, but soon after, like when you move a little bit, this will affect this diagonal. You move a little bit more, this will affect this diagonal. And in this case, it's actually affecting all the diagonals, but it's possible that one diagonal will be spared. For example, you are going from 1, 2, 3, 4, 1, 2, 3, 4, then you come 5, 6, 7, 8, so whatever was matching one, like the diagonal which was matching like this might be still okay because the pattern is changing on both x and y, but there would be just one diagonal that might survive. Everything else will break down. Okay, so it's enough, therefore, to check for periodicity. And we can check periodicity using uniform sampling. So we will do just uniform sampling on x and y, and we'll check for periodicity. And when the periodicity breaks, we have to somehow find the diagonal which might still survive and continue on that. Okay, sampling continuing on that. And in order to find, first of all, we have to do two things. One, like when we start doing the periodicity checking, we have to know what is the periodic pattern we are going to check, right? And also, like in order to find that, which are the good diagonals, like for which this periodic pattern is emerging. So we have to do these two things, find the good diagonals, because at some points, all of these diagonals might break, one of them will survive. So we need to know the subset of the diagonals. And we need to know the periodic pattern. It's just not enough to check that whether it's periodic or not. We have to check for the exact periodic pattern. Otherwise, it might fail. For example, it was periodic 1, 2, 3, 4, 1, 2, 3, 4, then it becomes 5, 6, 7, 8, 5, 6, 7, 8. If I don't check for the exact 1, 2, 3, 4 periodic pattern, I may not be able to tell that when the periodicity changed, all the diagonals are actually failing. There might be only one diagonal, and even there might not be one diagonal. All the diagonals could fail. So it's really important to check for periodicity, but also the periodic pattern. And in order to find that periodic pattern, every time when you are trying to do these, you have to spend some local sampling. So you have to look at locally around like k elements or order k elements. You have to see what is the periodic pattern I need to check next. And that's why you are spending this k query complexity per LC query. Just to find out which diagonals are good, like what is the periodic pattern. In order to find the periodic pattern, you have to wait for, you have to do this k query, local k query complexity per LC query. And that's exactly where the polynomial dependency on k comes up. And in fact, if you look at the subsequent works, which are also adaptive, which gets this n over k square, but k to the 4, k square, and all of these bounds, they are also like this kind of polynomial dependence in k comes in order to handle this periodic strings. So that's more or less how you can get like n over k, because you are doing this periodicity check. Periodicity check can be done just over the strings, but in order to find the periodic pattern, you are doing this local k steps, local k query complexity per LC query, and that gives you the polynomial dependency on k. And we get this n over k plus k squared because we have been able to reduce the number of LC computations to order of. And in fact, our algorithm from 2020, it not only solves this k versus k square, but you can use it to solve k versus k to the c. So let me skip this part because I think I'm almost running out of time. So let me tell you a little bit. How much time do I have? 5 minutes?
Yeah, 5-ish.
Yeah. So let me try to tell you a little bit about this algorithm, this n over k algorithm. So this is where you are doing just non-adaptive sampling, so no polynomial dependency on k. And that's also because we are not really looking at the string. So we are completely oblivious about whether the string is periodic or non-periodic. We are not looking at the string at all. Okay? So what we are going to do here, so we'll take these two strings and we will just break it into blocks. And we'll sample some of the blocks and we'll compare the blocks, compare the edit distance among these blocks. So that's what we are going to do. We are going to do this breaking of blocks, this decomposition of blocks will happen in multiple layers. So in the first layer, we decompose the string n into k blocks of size n over k. In the next layer, we decompose these blocks further, and now there are the blocks are size n over 2k, and there are 2k blocks. Then we decompose it further n over 4k, blocks of size 4k, and so on, and we continue going down. Okay? And at every stage, we sample blocks with a probability of 1 over k. So for the very first step, we'll or sample the blocks with probability log n over k. So the very first step, we will get probably sample 1 block. Then the next, we will sample 2 blocks. In the next one, we'll sample 4 blocks, and so on. And every time, what we do, if we sample x9 and y9, then we just compare the edit distance between the sampled blocks. And if the sampled edit distance is greater than k, then we say no. And if all the sample blocks, if we compare all the sample blocks and each of them is saying edit distance is less than k, then we say yes. So that's our algorithm. So we take these two strings x and y, we decompose them into these multiple levels. We sample blocks from every level. For every sample block, we compute the edit distance. If for all the levels, among all the sample like computations, we are always returning yes, so sample blocks edit distance is less than k, then we say yes, means we are in our overall edit distance is like, so we are certifying that our edit distance is below k squared. And if any one of them returns greater than k, then we say no. Okay, so that's what our algorithm does. So first of all, this part is really easy to see that if my original strings x and y had edit distance less than k, then if you look at any sample block and if you are comparing their edit distance, it has to be less than k. So you will be returning yes, because for every sample block you are computing edit distance, and that edit distance will be less than k because your overall distance is less than k. So that's great. So you'll be returning yes. The only case is like, suppose what happens if your edit distance is really large, greater than k squared? At that point, you really want to find at least one sample block for which the edit distance will be greater than k, so you'll be returning no. So the question is whether there is at least one bad block you can detect using this kind of sampling procedure over these multiple levels. If you can detect one bad block, then you are good. So let us consider the highest level, and let's see if the edit distance, suppose the edit distance is greater than k square, and not only that, these k square edits are distributed uniformly across all the blocks. If that was the case, then each of these blocks would be contributing k, right? Or more than k, so more than k square. So each of these blocks will be contributing more than k edits. So when you, whichever block you sample, it will return greater than k, so you will return no. But that happens only when your edits, more than k square edits, are all uniformly distributed. But it might happen that the edits are not uniformly distributed, but it's concentrated on like first half of the string. So if the edits are concentrated on the first half of the string, so suppose all the k square or greater than k square errors are concentrated on the first half of the string. Then if you look at this level, in the first half of the string there are at least k blocks. You will be sampling one such block. And for that sample block, you will be returning no. Right? So now it might happen that not in the edits are not concentrated in one half, but in 1/4 of the string. If the edits are concentrated in 1/4 of the string, then if you go to this level, again there are k blocks which are spanning this 1/4 of the string. So you'll be sampling one block at this level, and that will return no. So in other words, there is really no way to hide k square errors. At one level, there will be k bad blocks, which will be spanning these bad region, and you'll be sampling one block from that region. So that's kind of the main idea by looking at these various levels. And in fact, in Anduri and Onak's paper, they looked at one level. They looked at one level and they optimized what should be the level, what should be the block size based on whatever this k versus k square or k versus k to the c, whatever you are trying to do. Instead, here we showed that you do not really have to optimize the block size. Do it over all block sizes, and there is no way you can hide if there are too many errors. At least from one level, like you will be able to find, there will be a sampled bad block. Okay, so that's kind of the main idea. A little bit more formally. First of all, I have already shown you that if edit distance is really small, edit distance between x and y is less than k, then obviously I'm going to return yes because all my sample blocks will be good. But if we are returning yes, then why are we returning yes? Because the number of bad blocks across all the levels will be at most k, because we are sampling at a rate of 1/k. So if there are more than k bad blocks, I will be sampling 1. Right? So number of bad blocks is at most 1/k, at most k across all the levels. So what we could show that in that case, like if the number of bad blocks is at most k, then in fact you can decompose x and y using 2k good blocks. Good blocks means their edit distance is less than k. And if you can decompose x and y into 2k good blocks, that means the edit distance between x and y itself is less than 2k square. So 2k good block, each of them contribute k edits, so overall 2k square edits. And how you can think about it, like you can think about it, okay, so if this is a bad block, then in the next level I'm decomposing it into 2 halves, and I'm going to stop whenever I find a good block. Okay, so here this was a bad block, so suppose there are greater than k edits. You decompose it into 2 blocks. They are also bad, so you decompose it. Here it becomes good. Here it's less than k, so you stop over here. You don't decompose it further. You decompose the other ones. So here you decompose this one. One of them becomes good. You stop it over here. One of them is good. You stop it over here, and so on. And you go like that. What do you know? That if your algorithm is returning yes, the number of such bad blocks across all the levels is at most k. Now, if you look at the how many good blocks are there, so there are at most 2k of them, because each red block can originate 2 good blocks, the way the decomposition happens. So now you have a decomposition of x, and similarly same decomposition of y using 2k good blocks. Each of them is contributing k edits. So overall your edit distance between x and y is k square, at most k square. So that kind of is a proof why this n over k algorithm based on this multiple level of blocks work. And it doesn't have any polynomial dependency on k, but as you could see, it doesn't really look into the structure of the string. It's completely non-adaptive. So one thing that's a little annoying over here is like we are saying, hey, you have these two strings, you are decomposing it into blocks, you are look at these blocks, you say that you check whether the edit distance of this block is less than k, is greater than k, then you return no. But if edit distance is less than k, that's a good thing. And that is, so here what we are doing, we are using the fact that edit distance between any sampled block is less than equal to edit distance of the overall string. And that seems like a kind of a wasteful thing to do. You're just looking at one block, you're saying, hey, this edit distance is bounded by the overall edit distance. It would have been so nice if we could have said that, okay, if we could have something like, if we could have said, okay, sum over edit distance between xi and, if I sum over edit distance for all the sample block, that is actually less than x and y. Then it would have automatically actually give you much better query complexity than n over k. And that doesn't hold in general. But what we could do in our improved result, instead of looking at just the edit distance between the sample block, we look at what is called shifted edit distance between every sample block. So that's kind of the only change we make when we move from n over k to n over k square root of k. And this idea is kind of motivated by this 2003 paper, but we have to do some more work on there. And once you do that, in fact, previously what we are doing, we are sampling this block and we are computing the edit distance between the sample blocks. And in order to compute the edit distance between the sample blocks, we had to look at the entire block. We could not gain anything by, we couldn't sample or we could not run any sublinear algorithm on those blocks. But once we move to this shifted edit distance, we do not have to look, even on these blocks that we are sampling, we can actually employ some sublinear time algorithm over the sample blocks. And that helps you to gain on the query complexity, because now you're not looking at the blocks entirely, but you are looking at some kind of a sample of those blocks. And that helps you to get this 1 over square root of k gain on the query complexity. That's a kind of a very rough idea. So that's it. So that's, again, like, this is a reminder of the picture that we have currently about gap edit distance. It's pretty unclear whether this is the line where the adaptive algorithms may also be, this is the correct answer, because if you think about this red dot over here, this is a lower bound even for adaptive algorithms, not just non-adaptive. Though the algorithm they proposed is non-adaptive, but this lower bound is in fact holds for adaptive algorithms. So definitely, and this is then this orange line is the line for non-adaptive algorithms. So at some point, this is matching, like non-adaptive algorithms are matching the adaptive bound. It's just not clear whether this is the point where it should match or this is the point where it should match or where they should really match. So where does non-adaptive and adaptive algorithms meet? That part is not clear at this point. And most of it is coming from this polynomial dependency on k. So that's why, like, for all the adaptive algorithms, you are seeing this kind of trend. You are looking at 2022. This is how it grows. 19, 20, 24 results. All of these have this trend because of the polynomial dependency on k. So to understand whether really this polynomial dependency on k is required and where these adaptive and non-adaptive algorithms meet are kind of the main questions. And there are some questions about time complexity versus query complexity as well. But I think the most interesting is really to resolve that sky blue region.
Right, thank you. Any questions?
So I guess these algorithms are only like for the value of edit distance and cannot output the alignment because the alignment can be n. But I was wondering if it makes sense to study LCAs where you ask, who is this symbol?
That's a very good question. So non-adaptive algorithms actually cannot output any alignment. But the adaptive algorithms that I mentioned about this 2019 and 2020 results of ours, there you can actually have a succinct representation because you are just mentioning where the LC queries, approximate LC queries are happening. So there you can actually return the alignment in a succinct way.
Are there lower bounds for non-adaptive algorithms, or is it just?
For non-adaptive, this is a non-adaptive. Oh, we have a lower bound as well. So
for outputting the
the outputting no, that I don't. Yeah, that's a good question as well. Like if you have to output the alignment in some way, then whether these lower bounds can be strengthened for non-adaptive.
Okay.
I'm wondering, what is the nature of the data structure that does this LCE?
Oh, that uses suffix trees.
Oh, there's suffix tree.
Yeah.
Okay.
You can also do like some rolling hashing, like if you are willing to pay some log n factor. Suffix trees kind of give you the optimal 10, but if you want to do a log n, you can do like other stuff.
What does the lower bound look like? What kind of instances?
What?
The lower bound.
This is the lower bound.
Like, what does the instance look?
Oh, the instance. Okay, so our lower bound. Okay, so 2003 paper had a lower bound instance, and what we showed that if we get a better non-adaptive algorithm, then we will have a better algorithm than theirs. And in their case, I think what they consider is like taking two random strings. In one case, where the distance is large. In the other case, they just take one random string and it does a circulation. And now you have to distinguish these two cases. So that was kind of the hard instance.
Any other questions?
Yeah, so it would be really interesting to get some lower bound for the adaptive case. So for adaptive case, so that's kind of really like this adaptive and non-adaptive gap for edit distance is kind of really interesting, and we don't understand it fully.
Right, so looks like we have work to do. So let's thank Barna.